So today I'm going to talk about, this workshop is about, school is about dynamics, right? And combining dynamics and combining the tools of computer-assisted proofs to try to study dynamics. And well, one of the challenging aspects of dynamics are infinite dimensional dynamical systems. I mean, in the form of dissipative PDEs, parabolic PDEs. And another great challenge is to understand delay differential equations. And they're pretty hard to understand. And I started to work on them when I was at Rutgers in 2007, and I gave a talk about PDEs, basically about steady states of some simple parabolic one-dimensional PDEs and two-dimensional PDEs. And then Roger Nussbaum, who is basically, a god in the field of delay equations, and he came to me and he asked if I could study delay equations with this kind of techniques. And I had no idea because I didn't know anything about these equations. So basically I spent a bit of time at Rutgers and I started to talk to Nussbaum, and then also John Malé-Perret was there for sabbatical. So then I got to learn delay equations and some of the basics. And then I started to realize that most of the techniques that we've been developing for PDEs were directly transferable to study some aspects of delay differential equations. And basically it is in this direction that I will talk about that today. So I will show how to study simple delay differential equations. So I will focus on a specific type of delay equations, which I'm going to write right now. I'm going to write it as a scalar equation and only one delay. So basically, if you think of having a differential equation, so usually you have y prime of t depends on f of a function that depends on y only. That's an ordinary differential equation. So now I could actually think of having not only f, the right-hand side, depending on y at t, but it could also depend on the past, right? Where tau here is what we call the time delay. So tau here is positive, is the time delay. So there's a lot of work right now done on different type of delay differential equation, where now tau is, you can have more than one delay, that's called multiple delays. You could have systems of delay differential equations. So here I really think of f as being scalar. So that's a scalar equation, but that could be systems. You have people studying delays that are depending on the history. So basically state-dependent delays. So that's kind of very challenging, and this is basically at the forefront of what people understand theoretically. So I'm only going to focus today on this type of equations. There could really be more constant delays in that equation, but the ideas would be the same. Okay, so, and then there's a lot of motivation for these kind of equations. And I'm going to give you one classical example. And I think it's important to start with examples because, going back, delay differential equations do not have the same history as PDEs. You cannot go back all the way, centuries back in the past, but all the way to the 70s, then there were already great deal of attention in the application. So all the way back to 1955, then Wright, a number theorist, was interested in one equation. So that's basically going back to 1955. So Wright's equation, so that's Wright's equation. I'm writing it because I cannot not write it. And but I'm not going to talk about this one today. So it's basically an equation of that form. So it's alpha prime of t is equal minus alpha times y at t minus 1. So that's in the past. Multiplied by 1 plus y of t. In fact, this is the equation that dragged me in this field because there were, and there are still some important questions regarding the dynamics of that delay differential equation. Many open questions have been recently resolved and proven using the tools of computer-assisted proofs. So that's very exciting for our field. Some of the most, say, striking examples in the field of computer-assisted proofs in dynamics, Jay mentioned the Feigenbaum conjecture, proven in 1982 by Lanford. Also, there's the proof of Warwick-Tucker of the existence of the Lorentz attractor. And I think now we can say that another example is about the proof of Jones' conjecture and Wright's conjecture, which go all the way back to 1955. And there's a conjecture that says basically that for all alpha less than pi over 2, then the global attractor is actually equal to 0 for that problem. I'm not going to describe the details of this, but that was recently proved proven by Jonathan Jacket and Jan Bauer van den Berg using exactly the kind of tools that we talked about, using basically the radii polynomial approach. And that's a conjecture that goes back all the way to 1955. So I think this is pretty exciting, and that also shows you the breadth of the techniques and the range of applicability. Okay, so that's one example. As I said, I'm not going to talk about it, and it was introduced by Wright, who was a number theorist. He wrote a book with Hardy, a famous book in number theory, and for some kind of obscure reason, which I tried to find out more in details recently, it's not so clear to me, but there's a link between that equation and the distribution of prime numbers and the probabilistic approach to number theory. So for those of you who are interested in understanding the link with number theory, I actually have a bunch of references that I got recently, but I haven't had time really to go deeply. But that's one of the most famous delay differential equations. And another one, which I'm going to talk about at the end of my talk, is the one going back to 1977. That's in a paper published in Science by Mackey and Glass. It's called the Mackey-Glass equation. And that's the following. So let's say I have y prime of t equals minus beta times y of t plus alpha times y at time t minus tau divided by 1 plus y at t minus tau to the power rho here. So here I have a bunch of different parameters. So I have beta. Okay, so that equation models what? Models the concentration of white blood cell in a subject. So maybe I can write it. Models the concentration of white blood cells in a subject, a human. And so the different parameters here, they mean what? So beta is the rate at which cells die. Alpha is the growth rate. And now here's the interesting part, because in many aspects, it takes time for a body or for some biological process to understand that something is happening. So in that case, that's the tau here. So the tau models the time it takes for the subject to react to some given concentration. So it takes some time sometimes. So if you think about, let's say, gene regularity, gene expression, so sometimes you'll have proteins that will act on the DNA, but it takes a little bit of time for the protein to get out, do its job, and come back. So there is a time delay that is natural in many biological processes. And so that's definitely the case here. So that models the time it takes for the subject's body to react to a given concentration. Okay, and there's another parameter here, which is rho, and rho is it's basically a real number. So I'm gonna, not necessarily, it's a real positive number. And not necessarily an integer, and that's to model the fact that. So if you think of that function here as a function of, say, f of x equals x divided by 1 plus x to the power rho. So when rho is quite large, then what do we have? We have that there is a critical, there's a critical point for that equation here. So for instance, when alpha equals 2 beta, then y equals 1 is a steady state. So that's what we call a critical concentration. And that function, what does it do? So it goes all the way to, close to 1, and then it drops. So that's basically a function that will model the fact that at some point, if you go past a critical concentration, then it will just stop producing some cells. Okay? So that's kind of a model which has a non-trivial nonlinearity. It's not polynomial as it is the case here. And in fact, in order to solve that problem here, later on, I'm going to use the tricks of automatic differentiation to prove something about the dynamics of that equation. Okay, so these are the kind of parameters that are given. So in 1977, so Mackie and Glass, both from McGill, so they are colleagues of mine. I have the luxury of being able to see them once in a while and talk about delay equations with them. So they published in Science a paper about oscillations in that system. And in fact, that's one of the first models that portrayed chaos in infinite dimensions. So up to now, it is still an open problem to prove existence of chaos for that model. So if you think about it, it is a scalar problem. So if you were to remove the time delay here or even here, then you get a completely trivial scalar ODE for which the dynamics is completely understood. So just by introducing a delay here, then everything changes. And why is that the case? So question, why are DDE, so delay differential equations, so hard? And the fact is that they are naturally giving rise to infinite dimensional dynamical system. So why? So if I go back here, and I want to think of this as an initial value problem, okay? So if I want to think really of this as an initial value problem, so at time t is equal to 0, so let's say if I think of that, I want to solve this for t greater or equal than 0. Okay, so that's my time delay. So what do I need to know in order to move forward in time? In order to have a rule that tells me, given some data, I can completely move forward. So for an initial value problem in ODEs, all I need to know is the initial condition. That's a point in Rn. And once I have this, I know exactly where I go. So all I need to know is a given initial condition, which is in Rn. So that's why it's a finite dimensional initial value problem. So here, what do I need to know to move forward in time? Well, at time t is equal to 0, I need f of y at 0. Okay, that's at time t is equal to 0, as it is the case for ODEs. But now I need to go back in the past. And if I move a little bit further, then I need to know a point a little bit further in the past. So I need the entire history from the interval minus tau to 0. So that's my initial condition. And that is in a function space. It's function space of continuous function. So if I think of this as time t, and if I think of this as my solution, which I'm looking for, then I need all the way to minus tau, I need what we call the history. And that will be what I call the initial condition. Okay? So that's y0 here. So in order to really write down a well-posed initial value problem, I need to know that y of t will be equal to y0 of t for all t between minus tau and 0. Okay, so that's my initial condition is a function. Now if I want to move forward, then if you look at this problem, and if f is Lipschitz in y, then for all time t, so let's say now if I want to move forward, and I say, okay, so what if I now want to solve it, not for all time t greater or equal than 0, but just between 0 and tau. What do I need to know? Well, if you look at that equation, and if I know y0, then to determine the value of the solution for now, say t between 0 and tau, I can think of this as data now. This is exactly this guy, right? So this is data, so I can treat that as a non-autonomous problem, and that's now an initial value problem, and that's the data, and now I can completely solve that. And then I'm going to get what? I'm going to get, I'm going to use a different color, see? I'm going to get y1, right? So that's my y1. So what is y1? So y1 is the solution of that for t between 0 and tau, and with this initial data here. So, or in other words, I just treat this as a non-autonomous problem. Okay, so then I get my y1. And then to get my next segment between tau and 2 tau, then I do the same, but now this is, I'm solving that for t between tau and 2 tau, and what I use is the history of y1. So, and again, I can think of y1 as that guy. That's a non-autonomous problem. But if f is Lipschitz in y, in the first condition, then I can move forward. And that's why it really is basically, that method is called the method of steps. And that's really often used in delay differential equation to integrate an equation. So that's y2, and so on and so on. Okay, so, but the point that at each time t, then I need really the history. So the function space is really, so or the phase space, so if I come back here, so the phase space can really think of at any time that I'm here, then I need the history. So I can always shift that by, I can always shift back to the interval minus tau 0. So the phase space is really the interval, is really the function space, continuous function from minus tau 0 into R. So this is an infinite dimensional phase space. Okay.
It looks like a discrete system, right?
Well, you could think of this as a discrete system. If I had something slightly more complicated than this, I could have something, yeah. Now I really have a rule that depends on y of t and y of t minus tau. But to some extent, the way that we're approaching these kind of problems, you can really think of this as a map. That's true. Yes, an infinite dimensional map. In that context, if you think now of, we've been talking about Chebyshev or different type of methods to approximate solutions. So if you think of having the function y of 0 expressed in some basis, that's data for non-autonomous problem. So to get y1, you just need to solve a non-autonomous ODE. And on the level of the coefficients, so if you use Taylor or Chebyshev, then that's a map on the level of, you can think of a sequence, y0 is mapped to y1 under solving that ODE. So you can really think of it as an infinite dimensional map. Yeah. And in fact, this is a direction where we want to go in order to understand dynamics of non-periodic orbits. Because we have now, what I'm going to talk about today is essentially to prove existence of periodic orbits. So I will not necessarily use that philosophy, but that is good to explain the reason why it is really an infinite dimensional dynamical system. And not only this, but it's also useful to understand the similarities between the dynamics of parabolic PDEs and the dynamics of delay differential equations. So there's a lot of interesting, say, links between dynamics of PDEs and dynamics of delay differential equations. So, so DDEs and PDEs and, say, parabolic PDEs share many common features. So that's actually, I prefer the other pen is there. So I already mentioned the fact that they both give rise to infinite dimensional dynamical systems. So infinite dimensional dynamical systems. Another feature which is kind of interesting from our perspective is that they often give rise, a large class of DDEs and parabolic PDEs, they give rise to finite dimensional global attractors. So because of the somehow dissipativity nature, so finite dimensional global attractors. And these global attractors are made of the seeds of these global attractors are often steady states, periodic orbits, connecting orbits, invariant array, and so on. So the kind of machinery that we've been talking about, they're useful to try to get specific type of orbits in these infinite dimensional function space. But we're really looking for, from a dynamical systems point of view, we're looking for finite dimensional objects within these infinite dimensional spaces. Another thing which is very interesting is the fact that there is a regularizing effect. So So if you think of the heat equation, or if you think of, I mean, a brother of heat equations or different parabolic problems, dissipative problems, where you give an initial condition, then if the initial condition has singularities, or if it has, let's say, points where it's not smooth, then it will essentially instantaneously be regularized by the flow, right? So in the context of PDEs, let's say parabolic or dissipative PDEs, so then it's instantaneous. I mean, I have to say that this is really for dissipative. For hyperbolic, that's not the case. Okay, and now it's kind of interesting. Yes?
There's no way to solve backwards. I don't see. I'm trying to think.
Yeah, it's a semi-flow.
Yeah, I mean, this is a semi-flow, right? So I mean, I could actually write it. I mean, thank you. I mean, once you have an initial condition, you know how to move forward, but there's no way to go backward, right? So for the heat equation or for dissipative PDEs, then you know it's instantaneous. Whereas, so say y0, if y0 here is c0, what happened with y1? So okay, let me assume for now that f is c infinity. What will be y1? So if you think of this problem here, so now y prime for all t between 0 and tau, it's a function that depends on y, and it's also given by the history, which is c0. So now, basically, if you look at that solution here, then y prime will be given by I mean, it will have one, it will be c0, and then y prime will therefore be c1, right? So this is c0, that becomes c1. And now since that will enter here, and then f is c infinity, then at the next step, then I'm going to gain 1 degree of regularity. So that's going to be c2. So that's like, not only, so you can think of it as a map, but it's at so it's a discrete smoothing effect, right? So I go from c0, c1, c2, c3. So at infinity, what is nice is that solutions are very, very smooth, right? So let me write it, that for DDEs, it's like a discrete smoothing. But because of these smoothing, then they both, again, these class of problems, they both share the feature that bounded objects or bounded solutions, that is solutions which exist for all time, then they're smoother than the typical solution to a typical solution. So the implication is that bounded solution, so globally defined in time, are very smooth.
What do you mean by very smooth?
Well, okay, so for periodic orbits, so there's a paper by Nussbaum in 1973. Actually, this is a funny story. So I was at Rutgers, and okay, so as I talked about yesterday, we have to choose our function space in a way that it fits, I mean, the kind of problems we're trying to study, right? So for the Taylor, it was very natural to use a weighted L1. So for periodic orbits, if we use Fourier, then we have to address the question of decay rates of the coefficients. So I was at Rutgers, and I wanted to know if I could use, very fast decaying coefficients. And therefore, I wanted to know if the solutions were smooth. So then I went to the office of Roger Nussbaum. And I don't know if you saw his office if you went to Rutgers, but let's say it was a complete mess with a bunch of papers everywhere and then stacks. And so I entered in his office, and I said, so Professor Nussbaum, so I have a question. Are periodic orbits of delay equations analytic? So he looked at me and said, let's see. So he was walking slowly, and then he actually got a paper, and he gave me the paper. And actually, the title of the paper was Periodic Solutions of Functional Differential Equations are Periodic Solutions of Analytic Functional Differential Equations are analytic. So that the title was the answer of my question. How often does that happen? So for that class of problem, if you think of F as being analytic, then the periodic solutions are going to be analytic. And that's what I'm going to focus on today So in that case, smooth means analytic for this class of solutions. So I always found that these kind of common features are interesting because as far as I'm concerned, I really learned much more about PDEs before, and when I started to learn delay differential equations, and I mean, that was a whole new world for me. But then as you actually start learning more and more about them, then there's a lot of nice features that are common with PDEs. And yeah, I find it very nice. And in fact, this is quite important for us because the fact that these bounded solutions are very smooth, that allow us to actually design our function space in a way that they they incorporate the smoothness of the solutions, right? So that's why I'm going to use L nu 1 again, but now to talk about, to describe the Fourier coefficients of periodic orbits. Yes?
So besides periodic orbits, I guess bounded solutions are C infinity thanks to the method of steps, right?
Mm-hmm, mm-hmm.
But is it true that...
Well, then I don't, I mean, then maybe, I mean, the answer for periodic orbits I know, but for different type of I mean, if it's a chaotic solution on the chaotic attractor, then I mean...
But don't you get more smooth as you go? I mean, if it's a periodic solution, I guess it's the same along the steps, but if it's not a periodic solution, maybe it's more smooth towards the end.
Well, clearly it is smooth at infinity. At infinity, it is C infinity.
Oh, yeah, so
any solution of, I mean, if you have...
You're saying very smooth at infinity.
Yes, at infinity, but I mean that's what I'm saying, that at infinity, but therefore bounded solutions, so solutions which are
Something living in an attractor.
Yeah. I mean, for a periodic orbit, as I said before, there is a paper, I mean there's a theorem that says that not only you have C infinity, but you do have analyticity. Now for solutions on a global attractor which never close itself, then I don't know. Clearly there's C infinity if they're bounded, but at infinity, but yeah. I mean, I wouldn't be able to talk about smoothness for all typical, I mean, also, I don't know if we can really talk about analyticity for different, I mean, it's an interesting point. Yeah. Okay, so based on these, so basically now what I want to talk about is really to talk about how to use computer-assisted proof to prove existence of periodic orbits of linear differential equations via computer-assisted proofs. And the reason why, so because let's say many of these infinite dimensional linear differential equations have finite dimensional attractors, and it really makes sense to try to understand how these attractors are organized in one of the most important non-trivial dynamical objects in infinite dimensional dynamical systems are periodic orbit. And this is really also motivated by that paper. The title of their 1977 paper is Oscillation in Chaos in, I think, a cell models. But let's say they were very interested to understand oscillations because, of course, if you have some oscillatory behavior in production of blood cells, then it's interesting maybe to understand how it works. And these are very meaningful kind of solutions from the biological point of view. So biologically, it's interesting to try to really capture these orbits. And from our perspective, so mathematicians, well, we would like to be able to prove that they're really there, right? To compute some of them, and then to get proofs that they're really there. Okay, so I will actually focus, again, as I did yesterday, on a specific example. I will not go into so many details as I did yesterday, but I still want to consider one example, and the approach I'm going to use is in fact very general. But first I will consider a slightly simpler example, and then I will go on the slides, and then I will show some proofs for the Maclaurin equation using the techniques that Jay talked about, and using what I'm about to talk about in terms of Fourier expansion and Banach algebras of Fourier coefficients. Okay, so one example I want to talk about is a delayed van der Pol equation. And in fact, so that equation has been studied, since the 20s. But then afterward, people started to incorporate delays in that equation. And after that, Nussbaum considered a slight modification of it. So some people would call that a delayed van der Pol. Some people would call that Nussbaum's equation. So I'm going to write it down here, but let's say this is really close to van der Waals. So this is y double prime minus epsilon y prime of t times 1 minus the second, or the square of y, plus y at t minus tau minus lambda y of t equals 0. So this is, well, in that case, it's the second order equation. So if you wanted, you could rewrite that as a system, and then that would fall back all the way to the problem of the form y prime equals a function that depends on y and y of t minus tau. And in that case, f would just take value in R2. So I'm going to refer to that equation as equation number 1. And what Nussbaum did in 1974 so it's the following. So Nussbaum in 74, he showed that there exist periodic orbits of period greater than 2 tau for lambda between minus lambda 0 and 1, where lambda 0 is the min between epsilon divided by tau and epsilon 2 divided by tau squared. So 2 divided by tau squared. So the reason why he actually had to restrict his attention to that range of parameter lambda is because he needed to have a proof, a theoretical proof that the zeros of, basically that he could get the method of steps. So every time that you step, that he needed the periodic orbit to oscillate, but to oscillate for periods of time greater than the delay. So that was kind of necessary for his argument based on some fancy fixed point arguments to prove existence of periodic orbits. Yep.
Is there any relation between the delay and the period? I'm just trying to accept, for example, it doesn't have to be multiple or...
Sometimes, I will actually show you proofs where the period is shorter than the delay, and sometimes it's longer than the delay.
There's no integer relation?
No. Absolutely not. And in fact, when you go here, if you go back to the original results of Nussbaum, he needed basically to have that the period was greater than 2 times the delay. So let's say that was a strong assumption, and that was basically because he was using the methods of steps, and then he needed that to be giving him some information. But what I will talk about is absolutely independent of any restrictions. But we got inspired from his results, and we extended his results by showing the existence of some periodic orbits for lambda way below what he could do. But then, this is using completely different approach. But so inspired by that, we basically wrote a paper where we actually decided to use the techniques that I will talk about, and more generally. But I will focus on that example because that's simple enough to actually write down all of the map. Yeah.
You may say that this orbit is not really periodic. It's periodic for a time greater than minus tau, right? It doesn't extend to minus infinity. It's only forward.
Yes, but it's only forward. Yes, but you could still. If I give you a function which is periodic, defined for all time t, I can show that it satisfies that equation for all time t. So basically, that solution.
So these functions are defined also for
Yeah. But it's like if you have a dissipative PDE and you show the existence of a periodic orbit, and it exists for all time. So if you take an initial conditions very close to a periodic orbit, and you cannot go backward in time, but the solution, the periodic orbit makes sense. In fact, one of the strengths of this kind of approach is that, if we have a specific solution that we want to prove, say periodic orbit or even connecting orbit, if we make it the setup so that we forget about the ambient space, then we just restrict our studies for, say, periodic orbits. Even for ill-posed problems, I will show tomorrow some examples where we study, where we prove existence of periodic orbits for the ill-posed Boussinesq PDE. And in that case, there's no initial value problem, but yet there are some bounded orbits. So in that context, so we can prove existence of specific solutions, and nearby either there's nothing there's no initial value problem, or nearby there's no backward flow, but on the orbit they're globally defined in time. And in fact, this is really the idea that I'm going to use now. I'm going to look for periodic orbits by just plugging Fourier series and solving for the Fourier coefficients. And I'm going to get a map, and that map really only makes sense. The zeros of that is only giving me periodic orbits. I just forget about everything else. Okay, so that's the idea, right? So I already talked about my idea. So yesterday I was using a lot and Jay talked a lot about that today in terms of Taylor expansions. And now I want to move away from Taylor and I want to start using Fourier series. Okay, so say I'm interested in proving existence of periodic orbits for that model here. So what can I do? So I'm going to look for Fourier series. Well, I don't need to do that, but that's one way to do it. Okay, so I'm going to write y of t as an infinite sum of Fourier coefficients times e to the I k omega t, where omega is the a priori unknown frequency. So and in that case, well, yesterday I was writing things as power series and I was treating A as an infinite sequence of Taylor coefficients. Well, now I have the same notation. So A, and now instead of being indexed over n, it is indexed over z. And now it is a sequence of Fourier coefficients. Okay, so now I basically want to do exactly as I did yesterday. I want to plug that in to obtain an infinite dimensional map posed on the space of Fourier coefficients and apply the techniques that Jay described on the, yesterday in the first talk. Okay, so how do I do that? Well, first of all, I can see in my map here that I'm going to have a product. Okay, so I have to make sense of products. Yesterday, we talked about products of Taylor series. Well, yeah, that gives rise to Cauchy products. And now it's going to give rise to what? To discrete convolution. So let's say if you have y of t is given by the sum of ak e to the I k omega t, k is in z, and then if I have, say, u of t to be the sum or the Taylor series of bk e to the I k omega t, then I define their discrete convolution. So so y of t times u of t. I want to look for the Fourier coefficients. So clearly, this is still a periodic orbit of period 2 pi divided by omega, right? Because these are both 2 pi divided by omega periodic functions. I multiply them together. It's still periodic. And what I'm going to have a star b sub k of e to the I k omega t, where this is now the discrete convolution. So I'm going to write it down. So where A star B is the discrete convolution given component-wise by, so I have A star B. The component K is what? Is the sum K1 plus K2 equals K of A K1 B K2, where in that case K1 and K2 are in Z. Okay? In fact, this is quite easy to get that formula using inner products of, say, L2 functions. So you use L2, yeah, maybe for L2 functions. So you can take the inner product, you take 2, you multiply this and that, and you take the inner product with e to the I k omega t, so that's the integral, and then there's e to the minus I k omega t, and then basically you can write k1 here and k2, so the only non-trivial, that integral would be non-zero only when k1 plus k2 minus k equals 0, so that's why we have these restrictions here. So that formula is actually very easy to get. using the inner product of periodic functions. Okay, and now a nice feature is that now what I can do is that I know already that if I have a periodic orbit of a delay differential equation like that, as I said, I could rewrite it as a system and really have y prime equals f of y and y minus tau. And in that case, because of the result of Nussbaum, then I know that periodic solutions are analytic. By the Palais-Wheeler theorem, that means that the Fourier coefficients are going to decrease to zero, with a geometric decay. And then basically the decay depends on the strip in the complex plane, which is basically not going to contain the poles, right? So it's analytic, and it's periodic. So there will be poles in the complex plane, maybe or maybe not. And you take the largest complex strip, which does not contain any pole, and that's going to give you that length is going to give you the geometric decay rate. So if that length is rho, then the geometric decay rate of an analytic periodic solution will be a constant divided by rho to the k for the Fourier coefficients. Okay, and that's precisely the reason why now I'm going to plug that in there, and I'm going to look for the zero of a map, but in which space? Well, that's going to be in that space now, so it's going to be L nu1, same notation, and that's going to be the set of A, so Fourier coefficients, such that I'm going to use the same notation. The nu norm, by definition, is the sum over the integers of the, now in that case it's the complex modulus, ak, nu to the absolute value of k is finite. Okay, same, very similar structure. And as yesterday, well, in that case, I'm not going to prove it, but very similar proof. So L nu1 star is a Banach algebra, where now star is discrete convolution. Okay? Yep.
That's not analytic, that's just solvable.
Which one? This?
Yeah.
Well, if I consider the nu greater than 1, then I'll have, I will have,
K with the power.
yeah, that's the k, the k is an absolute value there.
Yeah.
In fact, that nu, you can relate the nu to the to this complex strip. I mean, I could do a proof of that. Yeah. No, these are definitely taking care of the analyticity. These are analytic norms for periodic orbits. And they are Banach algebra, so that's wonderful. Okay, so now let me move to a problem. So now I know how to multiply periodic functions. I know in which space I'm going to be looking for periodic orbits, knowing that they're analytic. So now I'm ready to actually take that equation and then move into the Fourier space. Okay, so for that I need to be able to take the first derivative. Well, in that case, this is easy, right? Just differentiate term by term. So of course I'm doing things formally, but in the end it makes sense because these are, I mean, if I take any derivative here, because of the geometric decay rate, and I have possibility to control all of these series, so they converge absolutely, so everything makes sense. But for now, let me do things formally. So it's ik omega ak e to the ik omega t. That's the first derivative. The second one is now basically the square of that. So that's minus k square omega square ak e to the ik omega t. Okay. Now I will multiply y squared by y prime. And one nice little trick here is the following. So observation. So if I take the cube of y and I differentiate it, then I have 3y squared times y prime of t, which means that y squared y prime of t is 1/3 times y cube prime. Okay, so when I will actually write down the Fourier expansion of that, then I can use that relation. It's going to greatly simplify the Fourier expansion. So basically from that, I know that y square of t times y prime. So since it is 1/3, so it's going to be the derivative with respect to time of the convolution of y cube. So now y cube is basically y times y times y. So now what I will have here, so if I would put y cube here, I would have a star a star a. That would be my the Fourier coefficients of y cube. But then since I differentiate it, then I have an ik omega appearing here. And then I have a star a sub k. E to the ik omega t. In fact, for that notation, it's an algebra, so we can even define that to be a cube sub k. Right? It's going to really condense. I mean, it's going to make a very dense notation. Okay, so that's the second. I mean, that's the term which I need to take care of. And then there's this term, and that's why basically Fourier series are so nice when it's time to study delay equations. If you're looking for periodic orbit, is that the time shift is actually diagonal with respect to Fourier coefficients. So now if you look at y at time t minus tau, then what is this? Well, you basically just plug t minus tau, so there will be a t minus tau, so there will be a e to the minus ik omega tau appearing times ak. So it's going to be e to the minus ik omega tau k omega tau multiplied by ak e to the ik omega t. Okay, so now I have basically all my Fourier expansions. So now I can actually go here and then write down that equation in Fourier space. So if I remove the 0 here, then what do I get? I get that this is equal to, and then I will have the sum over the k in z of what? Of something times e to the ik omega t. And I would just need to collect the coefficients. So yesterday I was collecting the coefficients in the powers of t to the n minus 2 and everything in front. So I had an infinite series and I needed that to be 0. So I said, well, for that to happen, I will impose that all the coefficients are equal to 0. That's going to be exactly the same thing here. Okay, so I have the second derivative. So I have minus k squared omega squared. And in fact, I'm going to collect everything that hits ak. So, okay, so that's this term here, so that's done. Now there's a minus epsilon prime times 1. So epsilon prime here is this, so it's minus epsilon times ik omega. So it's minus epsilon ik omega. I'm going to put that outside, and then this is now the shift, so it's e to the minus ik omega tau. So it's plus e to the ik omega tau minus lambda. So everything here times ak. Right? So this is the linear part. And that's going to be important because think about, again, about a dagger and a yesterday. So that's going to be the linear part, which will be unbounded. And that's what I'm going to keep in my derivative because this is basically going to be my diagonal part in my derivative. And finally, the only term that I didn't put is plus epsilon divided by 3. So it's plus epsilon divided by 3 times ik omega, so times ik omega a cube sub k. And I want that to be equal to 0. And that's basically going to be my map here that I'm going to solve. Okay? Okay, so what I want is that I want g sub k of omega and a by definition. And I'm going to define this by mu sub k. Mu sub k of omega. So I define it. So it's basically the linear part. It's mu sub k of omega times ak plus epsilon I k omega divided by 3 times a cubed sub k. That's kind of a simple map, right? And then I want that to be 0 for all k in z. So that's that's what I'm looking to solve. Yeah.
So, I mean, when you express the delay,
Yes.
you think that's like a regularizing effect? So, if you have some decay in AK, then
Well, that's on the inner circle, so
It's like a rotation.
yeah, it's a rotation. So there's nothing regularizing here. Yeah.
It's shifting.
Yeah.
It's just shifting.
There's really no regularizing. In fact, that is a problem when we have to differentiate with respect to the frequency, which we'll have to do because it is going to give rise to a non-bounded term. But the beauty of that is that now, I mean, that there's a k-square there, so the tail of my approximate inverse will have a 1 over k-square, so that will take care of these kind of bad terms. But yeah, unfortunately, that doesn't give me any contraction. Okay, so at this point, I have a map.
there is a minus sign here missing, right? E to the minus IK.
Did I?
Because you put a minus sign.
Maybe you're right. You're right. No, there's a minus. That's fine. Oh, you mean in the exponent? Yes. Thank you. Thank you. There's a minus. Yes. Yes. Okay. So now I have a map. I'm going to define it G of omega A. That's going to be G K omega A for all K is in Z. Okay, so what is the next step? So now we have a map posed on an infinite dimensional space. I mean, we have to bear in mind here that omega, the a priori frequency, is not known. So it's not like a system where I can fix a priori the period and then just look for it because it may not just be there, right? It's not like in a Hamiltonian system where I can fix an energy or I can fix the period and then look for this specific type of period. In that case, there's just no way to do that. So I really have to think of omega or the period equivalently as a variable. Okay? So I will solve for this. So the A is an infinite sequence of Fourier coefficients of the a priori unknown function, and G is my function that I want to find a zero. But I would like to be able to use the contraction mapping theorem to prove the existence of a periodic orbit. And in order to do that, I need to have some isolation. I need to have that in Fourier space. When I have a periodic orbit, it is isolated. But if you look at that, I mean, if I give you, say, assuming that A is a zero, so assume that A solves G of omega, I mean A omega, is equal to 0. Then if I define, let A sub delta to be e to the I k omega delta times ak, right? So the k is in z. So that's a point which, if A is in L nu 1, then that's also going to be a point in L nu 1, right? And when delta is equal to 0, I get my point. But when you think about that, what is this? This is just the shift. So these are the Fourier coefficients of y at t plus delta. So if I have a periodic solution, any time shift is also a periodic solution. That means that, I mean, there's a continuous branch of solutions in L nu 1 that going through a given solution. So if I think of L nu 1 as here, and if I take as A as my as a point in L nu 1, then there's a continuous branch going through that point. So basically, if I want to find, say, a ball that contains a unique solution using the contraction mapping theorem, there's no hope that I can actually do that. So that I need to isolate or to remove that. I need basically to slide that line and then to isolate a solution. So how do I do that? So people do that. I mean, it's a common practice. So to address this, we introduce a phase condition. there are several phase conditions that can be introduced. Some of the most natural ones involve a Poincaré map or a Poincaré phase condition. So in that context, so sometimes you know a little bit more about the orbits that you're looking for, and you can cheat and you can impose some simpler ones, right? So in that case, I'm going to cheat because the periodic orbits that are, I mean, we numerically computed a lot of periodic orbits in that equation, and they all were oscillating around 0. And the fact that they're oscillating around 0 means that we can impose an easier phase condition. I can just say, well, y at time t is equal to 0 is equal to 0. So if I have a periodic orbit that oscillates around 0, then if I impose that at y at t is equal to 0, I'm equal to 0, then you know I'm eliminating, at least locally, the time shift. Doesn't mean that that a shift would also be another, I mean, if I shift that there, that's also a solution, but that's a solution now there. So that's way further. So if I want to apply a contraction mapping argument by imposing this, there may be more than one solution to the same problem, but at least I will have locally a unique solution, which is basically what we need in order to apply these contraction mapping arguments, these very local ingredients. Okay, so I will basically append an equation, which will be in Fourier space, kind of the equivalent of that. I'm saying kind of the equivalent because there's a lot of room for this. So if you look at y of 0, well, y of 0 is basically when you plug t is equal to 0, so all of the exponential disappears, so I just have ak, right? But when you think of that, I mean, the derivative of that is going to give rise in Fourier space to an infinite line of ones. And, well, you know, that's okay, but for our perspective, it would be nicer if there was only a finite number of ones. So instead of doing this, I'm going to say that y0, instead of imposing that this is equal to 0, well, y0 is approximately equal to, given a large number n, it's this, right? So instead of having that y0 is exactly 0, I'm going to say, well, y0, which is now given a finite, I just choose a number. Let's say I can pick n equals 10, then that's going to be my phase condition. So that's a little bit off, but who cares? I just need to isolate the solutions. I don't really care of having a solution that goes through y of 0 is equal to 0. Sometimes it is important if you have, say, if you want to impose that you are in a fixed energy or that a specific quantity satisfies something at t is equal to 0, then we have no choice. In fact, I will talk tomorrow about the restricted four-body problem, periodic orbits, and in there we will have, because of the automatic differentiation, we'll have conditions that will need to satisfy at time t is equal to 0. So these will be similar equations, a bit more complicated, but we will need them to be equal to 0 for all, so then exactly, so basically I won't be able to do that. But
so you're setting that y at 0 is equal to a constant, right? So the constant would be the a here.
Yeah.
So it's a very small constant depending.
Yeah, depending on n, yes.
But you could also, even the solution was not going through 0, you can set it equal to another constant.
Yeah, you could be unlucky in that process and have that the solution is flat at 0 for a while, so basically you're just unlucky. Yeah. Okay, so basically I'm going to define this as eta of a, so that's my phase condition, this guy here, given a number n, okay? And now my map f, okay, and I will define x to be omega and a, and that's going to be part of my Banach space, which I denote by C cross L nu 1. And now I'm going to look, so that small x, so I'm going to look for zeros of capital F of x, which is equal to eta of a and g of omega a equals 0. So that's, again, my map that I'm now going to solve. And it's posed on an infinite dimensional Banach space. And then now that's the cross product. So now the norm, the induced norm, so I already told you what the norm on L nu 1 was. Now the norm on that space is basically, so if I look at the cross product, that's the max between the complex modulus of omega and the nu 1 norm of the Fourier coefficients. Okay. So now I'm at this point, so today I don't want to go into too much details about the the whole process, but I will, at least I want to show you the shape for the matrices because it's kind of easy in that case. Sorry?
Omega complex. Omega is real.
Well, okay. In my Banach space, I'm going to impose that it is complex. Because what I'm not going to talk about is how to make sure it is real. Okay? The thing is that that's going to be my Banach space because so my Fourier coefficients here, I don't necessarily have that to give rise. I mean, unless I impose some conditions, I need to impose that they are a complex conjugate, right? That A minus K equals AK conjugate. And if I do that in the function space, sometimes that leads to troubling, that leads to problem with differentiation. So we leave it open. And the nice thing is that that's our function space. That's fine. Everything. So we numerically compute. There is a small little defect, but numerically what happens is that we get that we fix that omega is real, and we impose the conditions, the symmetry conditions on the coefficients, which would give rise to a real solution. And now the nice thing is that that point is in my ball. Once I will have done the proof, that point has some symmetry, and T, my Newton-like operator, preserves that symmetry. So, and since you know that the solution, the unique solution, must be the limit of any point in the ball, I take that ball, my map preserves the symmetry, converge to that point, so that point in the limit, which is my fixed point, inherits that. So then it's only at the end that you get the proof that in fact this is real and that has the right symmetry to give rise to a real solution. But on the level of all the estimates and of the proof and of the function space, I don't do anything. It's only at the end that there is this nice theoretical argument that allows you to conclude. Yes, but at this point, I mean, I don't impose anything. And the reason why is that if you think of the phase condition here, then if I don't impose anything on the Fourier coefficients, then that could be complex. So then if I was going from R cross L nu 1 into C cross L nu 1, then I would not have a map that goes from a space to itself, so it would lead to some complication. But it turns out that this is not a problem. Okay, so all I want to do at this point is that, okay, so we are at the point where we have a Banach space, we have a map, and I want to solve the zeros, and I know that I can look for Fourier coefficients in this analytic space. And now, well, I want to apply the Newton-Kantorovich-like theorem. So I need an approximate solution. So as yesterday, what I can do at this point, I can keep just a finite number of equations here, a finite number of Fourier coefficients that gives rise to a large finite dimensional map. I apply Newton and I get numerical solutions. Yes? No, it was just okay. Okay, so the numerical the way to get the numerical solution is again using a finite dimensional approximation. What I want to talk about is basically a dagger, the approximate derivative. So now my coefficients are indexed over z. So I have really two directions to my derivative. So what I have is that I have a finite dimensional projection. I take the Jacobian matrix at an approximate solution, which is numerically computed, and that's my finite block here. But then I have two directions, right? So I have, I mean, this operator acts on a bi-infinite sequence. So that's 0, 0, 0, 0, 0, 0. Why? Because if I would take the true derivative, so say here, then what I would have, so that's the diagonal part, right? So if I take the derivative, I will have, because of the algebra, I will have 3 times a square k. Yeah, I mean, we didn't do a lot of calculus in Banach algebra, but believe me, this is exactly the same as differentiating polynomials. So if you actually differentiate this, then you're going to get a 3 in front and an a square. And these are the terms that will appear in the off-diagonal terms. You may say, well, there is a k in front, so that's probably going to grow. But no, because the a itself decreases so quickly, in fact, geometrically fast, that's going to win. So the derivative, these will all go to 0 as you move away from the diagonal. Okay? So that's why we can neglect them. I mean, we take a large finite dimensional projection, that's the derivative, we put a bunch of zeros, and we keep the diagonal terms here. And the diagonal terms are exactly these these unbounded terms from the linear part of the delay equation. Okay, so I leave. So basically, I have mu m plus 1 and all the way to infinity, and here I have mu minus m minus 1, and so on. 0, 0, 0, and 0. Okay, and for the approximate inverse, well, now I basically do the same. I numerically compute, as yesterday, a numerical inverse for that. That's a big matrix that sits on the memory of my computer. So let's say AM is an approximation of df m at the approximate solution inverse. So I put that in here. So that's AM. Everywhere I have zeros. And then I just put the theoretical inverse of these. So it's 1 over mu m, 1 over mu m plus 1, and so on. And the same thing here, 1 over mu minus m, 1 over mu minus m minus 1, and so on. So that's my approximate inverse. Okay, so again, it really comes from the understanding of the linear part of the delay differential equation. Okay, so now basically I'm going to stop in terms of the technicalities. I'm going to show you slides. And so for that problem, so Nussbaum originally, he actually, I think I have to, yeah. He proved some solutions for a continuous range of parameters where the parameters had to be restricted in some domain. And the assumptions again were so that the periods had to be greater than 2 tau, basically that he had to stay away above 0 for a period of time, for time greater than the delay, and below 0 for time greater than the delay. But he proved for continuous range. So what we wanted to do for that project is that we also wanted to get continuous range of periodic orbits. So there's a way to do that. We didn't really talk about this, and I will now mention that briefly. It's how to continue solutions. So given a solution at the parameter value, how can you continue that solution and get branches of solutions for problems? So now I'm stepping out of delay differential equations, and I'm really going back to the level of generality that Jay talked about in the first talk of yesterday. Now I have a map that is posed on some, I have a map F that is posed on some Banach space X, say, going into another Banach space Y, and it depends on the parameter. For the sake of simplicity, I'm going to consider just one lambda. It could be in R2, it could be in Rn. But let's see, this is exactly what I have here, because for what I'm going to talk about here, I'm going to fix the epsilon, I'm going to fix the tau, and that lambda is going to stay, as Nussbaum did, it's going to stay a parameter. Okay? So now say that I fix the parameter. I computed numerically a solution. I built my bounds. I built my A dagger. I built my Y0, Z0, Z1, and Z2 bounds. And I show that there is this small little ball that contains a unique solution. And say I change my parameter value, and I did the same. Now I would like to be able to go back and see, well, what happened in between? Is it possible to show that, in fact, there is a continuous range of solution, or, parameterized by my lambda, which are solutions of my equations. So in that case, for that problem, that would be a continuous branch of periodic orbits for that specific type of equation. And it turns out that with a mild modification of the general theorem that Jay gave yesterday, which is basically the following, and before that, you just have to realize that once I have a point, a numerical approximation, so which is obtained using Newton, and another one, then I can parameterize the line segment in between, right? I can just define x bar sub s to be the linear segment in between, and that's going to become my new center of the ball. But now it's going to be, I will want to do a uniform contraction in S between 0 and 1, so that I have a unique fixed point at every S between 0 and 1. And the theorem is basically the same. So if you look at the assumption, so now I have, now I'm making assumptions on F because I want to be able to conclude about the smoothness of the solution curve as a function of lambda. So I'm assuming that F is Ck it can go all the way to infinity, and then consider some bounds, y0, z1, z0, z1, z2, as before. The only difference is that now y0 will be a uniform bound, okay? So instead of evaluating the numerical defect at a given point, you evaluate it all the way, on the whole segment. So basically, y0 is a uniform bound for a times f of x bar at s, lambda s, for all s between 0 and 1. So lambda s is also a linear interpolation between lambda 0 and lambda 1. And x sub s is a linear interpolation between my 2 points that I computed. Okay, so that's a little bit different. So if I would just do that for s equals 0, then I would have the same bound as we had yesterday. No, it's just not a uniform bound. Z0 is the same. So I have a and a dagger. Z1 is the same. That does not depend on s. And Z2 now is also a uniform bound. So it is a uniform bound. So I want that to be, I could have written that B for all C, say, in the ball centered at x sub s. So it's essentially the same bound as J wrote, but now instead of being a uniform bound for that quantity over all C in the ball centered at x0 of radius r, now it's centered at x sub s. So it's true for all elements in the ball and for all s between 0 and 1. So these are the two extra type of estimates that you have to do. But once you're willing to do that, then the same conclusion holds. So if you define the same radial polynomial, if there exists a positive r for which this is negative, now there is more than just one solution. Now there's a curve of solution. In that case, it is x tilde that goes from, it's a function parameterized over 0, 1 with value in the ball now centered at, this is basically this, right? So now there's a curve that would be the red curve in the ball, which is now, it's a kind of a ball cross, it's like a parameterized family of balls here. And then there exists such function, which is ck. So it's as smooth as the function f that we started to work with. And that satisfies that f of x tilde s, lambda s is equal to 0 for all s between 0 and 1. And furthermore, these are the unique solution in the tube that I showed you here. So there cannot be another solution, another branch that intersect that tube.
So I guess that works very well when the branch is not too wild, right? Because then it's just a linear.
Yes, that just means that we have to take small, not so small time steps in the proofs. Yeah. In some sense, when you think about what Jay did in terms of propagating arcs, he was parameterizing, say, in Taylor, the initial condition. He was doing Taylor in time. We could also think of doing a more sophisticated parameterization of the solution curve, but that would be more work. But that would lead to some more, less trivial, say.
But you've done pretty wild branches. You just have to break them into lots of little pieces.
Yeah, that's the thing. I'm just saying that.
Yes, because the endpoints are basically, x0 bar and x1 bar numerical computations, right? So you can.
Yeah, as long as you take the delta lambda small enough, then it's pretty robust method. Yeah. It's just that you have to pay a little price. And the thing is that, of course, that can be generalized to pseudo arc length, because if you have a curve which now has folds, then you could do the same, but now instead of parameterizing the curve over lambda, then you would parameterize it over the arc length. And then the same business. It's just not, it's just for this problem we didn't need it. But okay, and then after that, what you can do is that, okay, so that's the theorem, and it's very, very similar. You just have to work a little bit more, but then you can have global branches, and you can show that along branches you do not have any secondary bifurcation. So that's kind of useful in some situations. And then what is nice is that because of the way that we actually build the radial polynomials, so we get a smooth piece of curve out of a proof, and say you could say, well, how can we? You know that this is ck or c infinity if your map that you're trying to solve is c infinity, and in fact, that map here is c infinity on the level of L nu 1. So if I get some solution curve, it will be c infinity as a function of lambda. So let's say I do one proof. So let's say this is c infinity. I do another proof which is c infinity. But how come? Then I could have, let's say, some points in between where I could have some non-smooth intersection. It has to connect because of the unicity. Because I have a proof on the left of a unique solution and on the right of a unique solution, and because of that they have to match. That's by.
points in the middle.
Hmm?
I can take points in the middle of the two. I can join.
Yeah, you can make an overlap.
Join.
Right?
Yeah.
Yeah, you mean like that?
No, I mean that I can take an x as 0
Like charts.
prime or something.
No, because it's unique.
It's unique.
No.
Oh, but
yeah,
the regularity.
Well, I'm saying that this division is arbitrary. You can make the piecewise solution.
Yeah, you mean I could change the lambda 1 to have, yeah. Okay, the thing is that in practice, that's one way that we could do that, but that would be a bit tedious, right? To change it and then to try to overlap, and then the thing is that now if you go back to the assumption, I mean, in fact, all of these estimates are uniform in S, okay? And what we verify in practice is that this is strictly less than 0, which means that by continuity of the bounds, when we construct these bounds, we make them continuous in S. And in fact, you could continue S for a negative epsilon and push it for a positive epsilon, and by continuity, that would still remain negative, which means that theoretically, because of the way that we build the radial polynomials, then you know that continues a little bit on the left, and that continues a little bit on the right, and then therefore they have to be smooth. So basically that never happens. And that's a byproduct of the technique. So basically with this, then we can just globalize branches. And then after that we can do pseudo-arc length and then get folds. We have also a paper where we did manifolds of solutions of steady states of PDEs, where now instead of doing pseudo-arc length, and now you do multi-parameter. Now you can do you can take a mesh or triangulation of a manifold in an infinite dimensional space, and now you do a uniform contraction about a simplex, and then you get a proof of a solution manifold, and then you can basically recover some smooth two-dimensional. We didn't do 3D, but okay, manifolds in function spaces. Okay, so this is a Z0 bound. Okay, this is doable. Same Z0 bound as yesterday, with the fact that we have these matrices, and then we have weighted L1 bound. So basically it's like a matrix, a finite dimensional matrix, and you take the weighted L1 norm, so that's all computable. Same thing with Z1. Okay, the Z1 for Fourier is more complicated. I do not want to kill you with the techniques involved in computing the Z1 bound for Taylor, but it is more complicated than in Taylor. It is more complicated than in Taylor. So Fourier is more complicated because when you take the derivative and you remove a dagger, basically when you think about Taylor for an initial value problem or the kind of problems I had yesterday, then when you compute a finite dimensional projection, then you compute everything, right? Because if you have a Cauchy product and you take the n component, it only depends on the lower Taylor coefficients. Which means that when I take that in Taylor, then I basically kill the a dagger kills a finite part of that. But for Fourier, that's not the case. Because in Fourier, if you think of the cubic convolution and you take the 0 Fourier mode, it depends on all the infinite modes, right? So if you take your derivative and you remove that part, then there's still a lot of terms that you didn't kill. So then you're left with some sort of weird convolution that has some zeros some places and non-zeros in the tail, and then you have to bound these terms. But that's all doable using the fact that we know that the dual of L nu1 is weighted L infinity, and all of that is doable. Okay, that's here. Okay, but so basically the details of all of that are now on the website, and then these are in some AMS notes that I wrote. Hopefully understandable, but we can definitely compute these Z1 bounds without too much pain. I mean, a little bit of pain for sure, but not too much pain. Okay, so here's the theorem. And in fact, I'm going to state it and I'm going to prove it. Okay, so this is lambda here. So, okay, let me state the theorem. So fix the delay to be tau equals 5 and epsilon to be 0.25. There's a branch of periodic orbits, or in that case I call it Nussbaum's equation, so that's this one. Parameterized over lambda, and then the range of periods goes from basically 3.2 to 5.2. So the period here is about 3.2. It goes all the way to 5.2. Yeah, the parameter range goes from minus 4.82 to minus 47.6. And for instance, you can see here that's the solution. That's the solution on the left. And now it's not so easy to see, but the distance between the zero is actually less than the delay, which means in that case that Nussbaum's method wouldn't apply here. Okay, so in that case, the distance between the delay is it's less than 2, and then here this is tau equals 5. So that's pretty far from the kind of results that the techniques of Nussbaum could do. And here, that's that periodic orbit, and this is still less than, so now it's 2.5. So let's say it's still less than the delay. So that's a new result. That was a new result. And then all the way here, then the distance is now about 3. And that also, so that whole branch is kind of new result. And now I'm going to do the proof. But the thing is that when I do the uniform contraction, very close, because I didn't do solar arc lengths, very close to these points, and I need to take a very small step size in the uniform contraction. So in order to do a quick proof, I'm going to start it here, and I'm going to show you the computer-assisted proof now. Okay, so MATLAB. Okay, so what this is going to do, so this is going to take a point, and then that's going to do the uniform contraction all the way from minus, in that case, I think, minus 4 point, I went a little bit closer on the right and a little bit more on the left. So that was a live proof. So that did 1,202 uniform contractions. And what we can see here is that at the very end, the delta lambda was 7 times 10 to the minus 5. So that's a very small step size. But if you look at, so that's the picture. So that's the delta lambda as I did the proof. Okay? So I started with a very small one because it was steep. So if I take a long step size, then that's it's very steep. So that was kind of not an easy proof. So that's the delta lambda as I did a uniform contraction. So these are this you could see. And then what you can see from the code, what you can see from the code is the fact that sometimes it fails. So for instance, the step 890 with delta equals 0.025, then it failed. So it was a too long step size, so my uniform estimates were just too coarse for the proof to go through. So what happens is that I reset that step and I decrease the step size by a little bit, and then I try to move forward. And then when it works, every time it works, I try to increase a little bit the step size, and when it doesn't work, then I decrease it. Okay, so I always try to get it longer, but there's like an adaptive step size choice, and that's what we could see here that's what we could see in this kind of function. But that's kind of fast. I think this is kind of fast, and these are qubit convolutions, so we're using the FFT to handle the qubit convolutions, and then for that, there's a nice feature in IntLab that handles the fast Fourier transform with interval arithmetic. Okay, so that's the first theorem, and here's another theorem. That's at tau equals 2, epsilon equals 0.15, and now the last on the branch, the period here is pretty long. It is more than 21.5, so that's a very long period. And here are some periodic orbits. So that's the period. That's a very big orbit. The amplitude is 6, but the period is more than 20. So that's a big guy. And we did that with one Fourier expansion. Okay, so I have like 5 minutes, I think, right, to talk about. 5 minutes just to talk about results involving the Mackey-Glass equation. So Jade made a very nice presentation about automatic differentiation, and here the same kind of ideas can be applied. So in that case, we used the tricks from automatic differentiation. We introduced that, to encompass it, that nonlinearity, then we let v of t to be u of t divided by 1 plus u of t to the power rho. So when I will differentiate that, there will be a u to the minus 1 of t, a u of t to the minus 1 appearing, and there will be that appearing as well. So I also define them, and when you define these new variables, then what you obtain is a polynomial delay differential equation. So the techniques that Jay talked about for ODEs, it really transfers directly to delay differential equation, and now that becomes a so that was cubic. So I guess in that case it becomes, so that's quadratic. 1, 2. Oh, I guess no. Okay, so that becomes quartic, right? 1, 2, 3, and 4. So that's That's now the dimension of, not the dimension, but the order, the polynomial nonlinearities, they get higher, but then, and we have a higher dimension also now that's a system, but everything is now polynomial. Why is that useful? Because we like our Banach algebras. So when we have products, then we can do the nonlinear analysis, and if we have products of functions, we can easily bound their product if we have polynomial nonlinearity. So that's why we like it so much. And we have to add some initial, I mean, these now, they need to be, so that's kind of my phase condition. U of 0 is equal to 1, because in that case, for Mackie glass, because of this choice of parameters, U equals 1 is equal to a steady state. Just plug it in, you'll see. And then because of that, at some point in the Mackie glass, then there are some half bifurcation oscillating around 1. So that's my phase condition. I'm imposing that U of 0 is equal to 1. And because of the choice, then you can see that V at 0 is 1 divided by 2. So that's why V of 0 is 1/2, and so on. So these conditions, I need them to be exactly solved. So now I cannot do this business anymore. They really have to be all the way to infinity. Okay? But now the idea is the same. I will use Fourier. But now I have these conditions to be satisfied, and they need to be balanced by some unfolding parameters. And what I do is that we impose basically just 3 constants there. And these are our unfolding parameters that can be justified nicely using the general theory that Jay talked about. But once we have this, here's the proposition. So let beta, the 3 unfolding parameters, so these are real coefficients. Then let U, V, W, and X a periodic solution of that system, which is the system I'm going to solve with Fourier and with the machinery I described. I plug that in, I will get a map in Fourier, and I will solve in some weighted L1 space of Fourier coefficients using the contraction mapping theorem. I impose that these are satisfied. So if that's a periodic solution, then U is a periodic solution of Mackie glass. And what I didn't write is that eta 1, 2, and 3 are going to be equal to 0. But okay, I mean, I guess that, well, that's kind of by definition. So if I have a periodic solution of that, then U is going to be a solution of Mackie glass. So basically, we apply our technique to that problem. We get our bound in L nu 1. That's going to give me a bound in L nu 1 for U, and, well, for its coefficient, and therefore C0 bound for the location of the solution. So here are some solutions. So what we did was to move in the regime in the Mackie glass where there is a chaotic attractor. So this is when, in that case, when tau equals 1.63, rho is equal to 10. So that's already kind of a steep nonlinearity. And that's a solution that was obtained with 70 Fourier modes in each of the components. So that's basically times 4, but then times 2 because I have positive and negative. So that's like 140 times 4. So that's maybe about 600 plus the unfolding parameters. And this is now larger. So that's 144 times 2 because I have negative indices. So that's about 300 times 4. So that's 1,200 Fourier modes, the projection here. And we did longer orbits. And this one, I want to show it in the phase space. So that's the nice picture that I have here. So there's a way to actually to visualize periodic orbits or solutions of delay equations is to put U of t on the x-axis and U of t minus tau on the y-axis. And if it's a periodic solution, then it will close itself. And that's a nice two-dimensional projection. In fact, these kind of projections are used a lot in the theory of delay equations to prove different type of solutions. And on the level of the global attractor, then that's kind of, we chose some projections, and then, the green one is the global attractor of Mackie glass. And, The conjecture, right, because that's still not proven. But what is proven is the red and the blue ones. These are computer-assisted proofs, and the R's from our proofs were about 10 to the minus 9. So in the neighborhood, in a C0 neighborhood of 10 to the minus 9, about the red orbit, there is a true solution in Mackie glass, and the same thing in the blue one. And in fact, that's quite nice because I started to work on delay equations because Roger Nussbaum asked me after one of my talks, as I said before, and what he asked me was if I could prove coexistence of periodic orbits in Mackie glass. And that was in 2007. And at that time, I couldn't do it because of the nonlinearity. I could only do polynomial nonlinearity. And then I met that guy, and he taught me a lot of stuff. And now I can talk about it essentially 10 years later. So it's a nice close-up it's a nice ending. And on this, I guess this is it. Thank you.
So any questions for Yanni? So can you explain your last picture? Where is that happening?
Well, so Mackie glass is an infinite dimensional dynamical system. So when you integrate it, then you have to visualize somehow. So on the left here is just a projection of the orbit, where I take u depending on t, and then I take it with u of t minus tau. So maybe that one is u of t, ut minus tau, and ut of minus 2 tau or something. I don't know.
No, it's like some point in the middle, because minus 2 tau, it doesn't work if it's...
Yeah, I don't know, or maybe some point in the middle. Okay, I have to go back in the... But it's a finite dimensional projection of the...
That three-dimensional picture, I just don't see what it's happening.
So that's the thing. So it's a finite dimension. It's an embedding in a... the object lives in an infinite dimensional space. So the claim is that this is a finite... as I mentioned before, there's a lot of proofs for some given delay equation that the global attractor is finite dimensional. For Mackie glass, it's not well understood. So we believe that the global attractor is there and that it is finite dimensional. And people visualize it by projecting. It's like if I was to simulate some PDEs and I use Fourier coefficients, I could just take 3 or 4 Fourier coefficients and look at it in R3. So in that case, that's a two-dimensional projection of these two orbits. And now I could look, but as Renato said, it's probably like u of t minus tau, and the third dimension is maybe u of t minus tau divided by 2 or something. But you have infinitely many projections, right? So it's just a nice visualization of that, but you can see that that's not so trivial, the apparent global attractor. Yeah, and the next step would be to now parameterize the stable and unstable manifolds and show transverse intersection between some of them, and that would be the first proof of chaos in Mackie glass. And yeah, that's one of the things we're working on. Yes.
Ok, si no hay más preguntas, te agradecemos a Jean Philippe.
Okay.